She's a PhD student in Liège, and today she's going to talk about two applications of the composition of a two-tape automaton and a weighted automaton. Please, Célia.
Thank you, Manon. So this talk is a joint work with Émilie Charlier and Manon herself. So in this presentation, I will talk about a composition of two types of automata. So first, I want to define the two automata I will work with. To do so, I just want to say that all along my presentation, A and B will be two alphabets, and I will consider a symbol, $, not belonging to A neither to B. So this $, will be used for the padding symbol. So I will just explain it here, but and I want to precise that in this presentation, I will denote A substack $, the alphabet A, where I had the symbol $, itself. Okay, so the $, symbol means that I will pad the couple of words with the $. So if I want to talk about the couple of words U and V. I can talk about a couple of words, but I can't say that it's a concatenation of a couple of letters. So to be able to talk about the concatenations of letters, I just need to pad the smallest word between U and V with padding $. So that is what is written here. Why I need that? It's to talk about two tape automata. So I will consider a two tape automaton that is just an automaton, but we were working with pair of letters. And so the edges are just labeled with pair of letters. And I will say that a word U over A has an image V if the pair of words UV padded is an accepted word in the DFA I'm considering. So that is the first type of automaton I will consider. So for example, that will be the two tape automaton I will consider all along my presentation. It is just an automaton where all the possible pairs of letters are written, except that the $ can be read only at the first step. So if I consider the words, I'm working with word over the alphabet A, B. And so we can check that the words that are images of U are the words where the length of U and V differ by at most 1 unit, because we can just put the $ in the first component or the second one, but just only at the first step while reading something in this automaton. Okay, the second automaton I will work with is the K automaton. So that is an automaton with weight in the summary K. So weighted automaton is an automaton where I consider a set of states, an alphabet, but each state have a mapping I and T. That is the initial and the final weights associated to the state. And there is also a mapping E, mapping each transition to a weight. So what I call it a transition is just a triplet, P, Q, where P and Q are some states, and the letter B. The letter B is the label. And so the image of this triple by the mapping E is just the weight I will associate to the transition. So here we can see that there is K automaton with two different states, and the initial state is this one because that is the only one having a non-zero weight, but we can have more than one initial state, but it's not the case in this example. And for the final weights, we can see that this state is state final. Okay, so as usually, you can draw a path on an automaton. So here a path is just a concatenation, a sequence of transition. The weight is the product of the weight of its transitions, and the label is the concatenation of the label. So nothing new. A path is said initial and final if it starts in an initial state, and final if it ends in the final state. But what is new in this slide is just because we talk about the weight of a word, and the weight of a word is the sum of the weight of all paths labeled by the word I'm considering, but I multiply this weight by the weight of its initial weight and its final weight. So in my example here, I can check that the weight of a word over the alphabet AB is the length of the longest suffix made of A's. So for example, if I consider the word ABAA, I know that before the B, I can't go to Y. So I'm obliged to AB, but then I must read AA, and I have two possibilities, AA or AA. So there is two paths labeled by ABAA that are initial and final. Both of them have weight 1, so we have that ABAA as the weight 2. We can always, without loss of generality, modify the K automaton B in order to have only one initial state and no incoming transition. So that is what I'm doing here. But what in the following, I will talk about the modification of B. So this modification will be this modification, but I also will add a loop of label $ of weight 1 in over this new state. Why I'm doing that? It's to be able to read some words where with some dollars followed by a word V over the alphabet I'm considering. And this type of word have the same weight as the word V itself. So that is why I'm doing that, but it will be more clear in a few minutes. And then a question arises. So if I'm considering a two-tape DFA and the modified K automaton, so the modification I just said, the question is, can we compute a new K automaton over the alphabet so the first alphabet I'm considering, such that the word U over A has weight as equals to the sum of the weight of its images, so in B, in the K automaton B. So for example, in the two automata I'm considering, here, for example, the word A has these images, so the words having a length 0, 1, or 2, because A has length 1. And all of these, we can compute their weight. So the longest suffix of made of A, so 0, 1, 0, 2, 0, 1, 0. And so we want A to have the weight 4 in this new K automaton. So the idea is to define the composition of these two types of automata. So I will take a U over the alphabet A. I can go through the two tape automaton to understand which words over B are the images of U. These words I can go through the K automaton B to understand their weights. And then I want to define a composition associating to U the sum of the weights of the images of U. Okay, so I will define this composition. So here I wrote again the two automata I want to compose. And I will define this composition. So note that here I will consider a B such that it is already modified. And the composition will be a type of product. So I will make the product of the states of each automaton. And I will add one more state called alpha. You will see later the role of alpha. The initial weights and the final weights are quite easy. That means that for a couple of states, it is initial if it's initial in both components. So that means that in A, I have only one initial state and one initial state in B. So the initial state is this one. And it has the weight, because we're working with a K automaton, to be the same as in B. No other state is initial except alpha, that we make it initial. And for the final weights, that is the same. The state QQ prime is final if it's final in both components. And if yes, we associate the weight associated to the Q prime on B. So that is here the example associated to these two. So it's not the most difficult part. So I will go through the next example. Here I'm defining the transitions. So the easy steps is that nobody can go to alpha, neither alpha itself nor any other state. And I can define the weight of a transition between Q1, Q1 prime and Q2, Q2 prime with the letter A as follows. So I will first check all the letters in B, so B dollars, all the letters that are the images of A between the state Q1 and Q2, Q2. So that is these type of letters. For all of these letters, I will compute the weight of this letter in the K automaton B, and I will between the states Q1 prime and Q2 prime. So that is how I define these transitions, the weight of the transitions. So the sum here is what we expect to have the sum at the end of the composition for the weight. So here we can do the example. I'm going here. So from 1 to 2, for example, dollar have two images, A and B. But from I to X, A has weight 1 and B has weight 1. So that means that from 1i to 2x, dollar will have weight 2 because we sum the two weights. Still from 1 to 2, but from I to y, we have that A have weight 1 and B have weight 0. That means that the dollars between 1i to 2y will have weight 1. So that is these two examples. Okay, so I'm quite okay, except that I don't have defined the weight of the transition from alpha. So nobody can go to alpha, but alpha can go to some states. And I will define the transition from alpha to other state like this. So I will sum the weight of the path labeled by some dollars followed by A from the initial state to the state I'm considering. So I will also multiply that by the initial weight, but it will be more precise in the next slide, because like this, it's like an ugly definition, but here it will be more clear. So alpha can go to 2x because from 1i, so the unique initial state, we can go to 2x with the word $A. That is the only possibility. So we will multiply the initial state by 2 times 2. So we have the transition from alpha to the state with the weight 4. We have the same for B, but from alpha to 2y, it's a little bit different because we have the path $A with the weight 1, but we also have the path here $A with the weight 3. So we multiply, we add 1 plus 2, we have 3. Sorry, I have said 3, but it's 2 here. So 1 plus 2 is 3, and we multiply that by the initial weight, we have 3. And the same for B. Okay, so the only strange thing in this definition is the rule of alpha. And the state alpha, what we want we want Célia today to do is that we want the state alpha to bypass the leading dollars. I mean that if U and V are, V is an image of U, then the couple some dollars before U and V will be accepted in A. So I must read this word to understand V and then read V in B. So until now, if I do not have the transition from alpha, I must have a pass with this label instead of U in the composition having the same weight as I want. So here the alpha bypasses these dollars. The other thing I have done before is adding the loop dollar with weight 1. It was just for having the right answer for the words that are images of U, but with smaller length. I mean that if U is, V is an image of U and V is smaller than U, we have some padding dollars before V, but this word can be read in the modified K automaton V such that we can read the dollars in the loop I added, and I just multiplied the weight by 1. So the state alpha is for the images greater than U, and the modification of B is for the images smaller than U. Okay, so that is the composition I'm defining, and we have the first theorem I want to say is about the link between the relation and the two tape automaton. It's quite easy to see. Sorry, I must. Okay, so it's quite easy to see that between the notion of a two tape automaton and the notion of relation are quite related. So I mean that if I'm considering a relation from A to B, a relation is said synchronized if there exists a two tape automaton accepting the languages of padding pairs that are related. So for example, in my two tape automaton, it's a relation between the alphabet A, B to itself, and two words are related if their lengths differ by at most 1 unit. So there is a link between a synchronized relation and two tape automata. There is also a link between formal series and K automata. So a formal series is a function from the words over A, and that associates its coefficient in K. So each word has a coefficient. And of the series that are K recognizable are the series for which there is a morphism of matrices and two matrices such that the coefficient of W in S can be expressed thanks to multiplication of matrices. And we have a link between the K recognizable series and the series that are recognized by a K automaton. So a series is recognized by a K automaton if and only if it is K recognizable. So we have this notion, and in my example, this K automaton just recognize the series mapping each word over AB to the length of its maximal suffix made of A's, as expected. So we want to use our composition, so we must define a composition between a relation and a series. And so if I'm considering a relation R and a series S, such that the number of words related to a word U is always finite, then we can define the composition of S and R, mapping each word to the sum of the coefficients of the words V in relation with U. So that is quite the same diagram I was working with for the automata. So as we can expect, our composition of automata will be used to prove that if I'm considering a synchronized relation and a key-recognizable series, then the composition of these two is still key-recognizable. To do so, what I must do is just considering the two tape automaton associated to the synchronized relation, the key automaton associated to the series S, modify this key automaton, construct the composition of these two, and then I must project at the end on the alphabet A, like, because I don't want any dollar anymore. There is also a small, tiny change I need to do for the final weights of the initial state IA and IB, because there is a tiny problem for the empty word. But doing that, we have that the obtained key automaton recognizes a series that is a composition. So this theorem is the theorem in terms of the automata, but the two applications I wanted to talk about today is about regular sequences. So I will not go very in the detail, but the first application is about regular sequences in abstract numeration system. So an abstract numeration system is just a triplet of a totally ordered alphabet and a regular language over this alphabet. Thanks to the order over the letters, we can order the words on the language L, thanks to the radix order so I means that I will before order the words by the length and then by the lexicographic order between the words of the same length. So that is an abstract numeration system. And there is a representation function associated to this type of numeration system. So the representation maps any non-negative integer n into the nth word in the language L. Here, be careful that we start by indexing by 0. So we will do the example now. And before doing the example, I just want to define the value function. That is the reciprocal function of the representation function. So it maps any words over the language to its index in the regular language. So here for the example, we have the most famous abstract numeration system, that is A star, B star. The representation of 7 is the word AAB, because we have 0, 1, 2, 3, 4, 5, 6, 7. So that is the word AAB. And the value of AAA is then 6. Note that the value of BA is not defined because the value function is defined over the language L, and BA is not over the alphabet A star, B star. Okay. So knowing the notion of abstract numeration system, we can talk about regular sequences over this type of numeration system. So a sequence is SK regular if the formal series here is key recognizable. So the formal series is defined over the words that are in the language L, and we will associate to these words the coefficient f of n if the word I'm considering have value n. Okay, so that is a notion of regularity. There is another notion over the sequences that are synchronized, but these are synchronized between two abstract numeration systems. So if I'm considering two abstract numeration systems, and S, Sn, and S prime, a sequence is say synchronized if the pairs of representation of n and f of n over the abstract numeration systems S and S prime padded is a regular language. So as you can expect, the notion of regularity is linked with formal series. The notion of synchronized sequences is linked with relations, so synchronized relations. So it's easy to see that if F is a S prime synchronized sequence and J is S prime regular sequences, then the composition of these two sequences is still regular. I just want to say that if I'm composing two synchronized sequences, it's easy to see that the composition remains synchronized. But it is well known that the composition of two regular sequences is not necessarily regular. So that is already the case for the numeration in base B. So here, knowing that any synchronized sequences, in any synchronized sequence is regular, we think the most we can say about this type of compositions. Okay. The second application is still about regularity, but not over the general framework of abstract numeration system, but I will consider the numeration system that are positional. So the U numeration system we all know. So a sequence is defined to be regular in the same way, except that we take the representation over the numeration system U. But since that the representation in U are made of the alphabet from 0 to some integer, we can extend the U value function over all the words over this alphabet. And so we can have an alternative definition saying that I will consider not only the words over the regular language verb U, but I will consider all the words over the alphabet, and I will associate to this type of words the coefficient that is the F value function of the value of the word. So that means that any word having the same value as a representation, the representation of n will have the coefficient F of n. Okay, so there is two alternative definitions. And in the base B representation, it's easy to see that these definitions coincide because we have only the difference of the representation of n and any word having the same value that are the leading zeros. So it's known that these two definitions coincide for the base B representation. But in the U, it's quite more different. But for any Piso numeration system that we know that the normalization is effectively computable, that means that there is a Two Tape Automaton mapping each word U to its normalized word. That means the greedy word having the same value as U. So from U, we can go to its normalized version. And to this normalized word, we can compute the weight S over the series recognizing this series. So thanks to this notion of composition, we can prove that the two notions I have for the regularity over Piso numeration systems are equivalent. So I just talked about the two applications I wanted. Here's the references I want to underline, because it's the two references of the paper with Emily and Manon that we submitted. This one is already published, and the composition of the two automata and the two applications are in these two papers. I just want to say that in this paper, we use the general framework of D-dimensional alphabets, so and D-dimensional Piso numeration system, etc. But to be more clear in my presentation, I have done everything in dimension 1. So thank you. That's all I wanted to say.
Thank you, Célia, for your talk. Do we have a very quick question maybe for her? Because we're running out of time here. Yes, Christophe, yes, you can talk, of course.
There is a theory of image of non-commutative rational series by rational transductions. By the theory is due to Fliess and mainly Jacob, and you can find things like on this in the book by Saloma Soitola. I would not be surprised if the case of synchronized relation could be obtained as a consequence of this theory.
Okay, we have looked a lot on the composition and operation between automata, and we haven't find this operation particularly, but we can check again.
Mm-hmm.
Thank you.
Yes.